We need to start by explaining how the basic containers for information in a classical computer differ from those in a quantum computer. The smallest piece of data you can store in a regular computer is always either a 0 or a 1. This is called a bit. Think of it like a coin lying flat on a table. It can show either heads or tails. In a quantum computer, the smallest piece of data is different. Imagine it not as a still coin, but as a spinning coin. While it's spinning, it's not just heads or tails. We can describe it as having, say, a 30% chance of being heads and a 70% chance of being tails when we stop it. Of course, it could be any combination, like 10% heads and 90% tails. The outcome isn't predetermined, it appears randomly. As long as it keeps spinning, it isn't fully heads nor fully tails. Only when we force it to stop and land on the table does it decide to become a definite heads or tails. We call the smallest piece of data in a quantum computer a qubit. If we place a few of these spinning coins next to each other and start controlling them properly, we find that they begin to influence one another. It's as if they feel each other's presence and affect each other's spin. Because of this interaction, when we finally force all the coins to land at the same time, it turns out that their outcomes are no longer independent. Some heads-tails combinations appear more frequently, while others appear less often. This depends on how the coins influence one another during the computation. Consider this scenario. We have a massive set of information, for example, a billion numbers, and we want to find the one correct answer among them. A classical computer would typically process numbers one at a time in a straightforward approach. It might take the first number and run a calculation, then the second, the third, and so on. Of course, classical computers can also use clever methods to search faster than checking each number individually. But even then, with truly massive unstructured data sets, the smartest tricks still take a very long time. If we had even more numbers, say a trillion, checking them could take ages. In some extreme cases, maybe even 100 years. A quantum computer approaches this differently. Let's stick with our spinning coin analogy. Suppose we have 30 such coins. This gives us over a billion possible heads-tails combinations. Each combination can represent one number from our billion-number data set. A quantum programmer writes a program that doesn't check each possibility one by one. Instead, it controls how these coins influence each other while they spin. After this interaction has properly shaped the situation, the measurement happens. All coins land on the table simultaneously, showing a specific set of results. It's a bit like carefully arranging waves in a pool of water so that a single massive wave builds up right over the treasure, while everywhere else the water becomes perfectly calm. If the program is well designed, the incorrect combinations have a very low probability, and the correct one appears with a high probability, often around 90%. The algorithm is designed so that a single run has a great chance of being correct. Sometimes it's run a few times, mainly to confirm the result and minimize the impact of any errors. In other words, a quantum computer doesn't check answers sequentially. Instead, it steers the probabilities so that the right answer becomes the most likely one to appear. For specific types of problems, this can radically shorten the time needed to find a solution.